All right, so we discussed AC versus DC. All right, go back to flux. What's flux? That's the amount of magnetic field intercepted by an area. And all of a sudden I'm looking at it, I'm thinking, okay, so let's add on to it. All right, so that's the strength of the magnetic field. Component of the strength of the magnetic field along the direction of the area. Okay, so this is a better description of it. All right, so what is the Faraday's law? Change in flux induces current. All right, speaking of change in flux, you can vary the strength of the magnetic field inside the area. So that's going to induce current. Or you can spin the area inside constant magnetic field. So that's going to change the strength. That's going to change the area exposed to the magnetic field. All right, I'm going to change the notations a little bit, keep these as vectors, or else the explanations kind of become somewhat weak. All right, so area as a vector, obviously you're just changing the area exposed to the magnetic field, so that induces current. All right, so change of flux, does it induce voltage or current? Obviously it does induce voltage, and voltage is what drives current. Okay, by varying the number of turns in a coil, you can adjust the voltage, you can also adjust the current. That's it. All right, so how's current generated? Change of flux. All right, and so in generating current, by what means the coil is spun? By mechanical means. All right, so running water, rising steam, wind. All right, so that's as far as we got. So let's get back to 13. We'll jump back. All right. Okay, so Lenz's law is something that we'll get back to. Okay, electromotive force for a power generator. Okay, we had a few discussion regarding this one. All right, so we got a coil which is being spun inside a constant magnetic field. That's what we got. So in essence, we're changing the flux. It can have a number of turns just like this one is. So it's going to give you an electromotive force. All right, so we get an expression for the flux. This is a scalar expression of it. Notice that this angle is going to change within a certain time period. So how fast the angle is changing can be represented by the angular frequency or angular speed. And then we end up doing the algebra or the calculus in our case, and then we came up with an expression, mathematical expression for the electromotive force. What's happening as you start to spin this thing is electromotive force keeps changing direction. All right, it goes one way, reverses direction, goes the other way, maximizes, goes the other way, maximizes, changes direction, and maximizes, and so forth. All right, so which means that the electromotive force does this. If this is a wire, electromotive force keeps changing direction, this way and that way. And it does it a number of times per second. Omega represents that. All right, so epsilon naught is going to represent the maximum value that it's going to have. All right, so we should just represent that. All right, so this becomes the maximum value that it's going to have. So the maximum electromotive force is going to depend on a number of things. It depends on how fast you spin this. If you spin it 60 times per second, it's going to have a certain value. If you do it 90 times per second, this thing is going to be larger. If you do it 500 times per second, this thing is going to be larger. All right, so you can increase the electromotive force by actually varying the speed, angular velocity, and angular speed of it. So faster this is spun, the larger the electromotive force is going to be. Stronger the magnetic field is, larger the electromotive maximum value is going to be. Larger the number of turns, larger the electromotive force is going to be. The maximum value is going to be larger. All right, so those are the contributing factors. And then we talked about the RMS values. All right, electromotive force is what drives current. Okay, notice that they're going to be in phase. As this is going up, the current is going to go up. As this is going down, the current is going to go down. Electromotive force is what drives current. Your average electromotive force is going to be 0. Your average current is also going to be 0. On average, you get 0 current. On average, you get 0 voltage from the power company. So the power company does not charge you for current or voltage. They charge you for the power. That's the reason why it's called power company. All right, so this is the power, which is generated by the power company. And notice that if you're looking at the power goes up and down. So it's got a maximum value, which is going to be right here. It's got a minimum value, which happens to be 0. So instead of charging for the maximum or the minimum, they charge you for the average. So average of this is going to be half of this value. That's what it means. All right, so this half of that becomes like that. All right, and this 1/2 is expressed in terms of 1/2 could be expressed in terms of 1 over square root of 2 times 1 over square root of 2, and then one of the square root of 2 is going in front of the maximum current. The other is going to go in front of the maximum electromotive force, and this becomes an RMS value for the current, and this becomes an RMS value for the electromotive force. Okay, so when do we use the RMS values? use the RMS values when we need non-zero averages, right? All right, because on average you get zero current and on average you get zero voltage. So if you're interested in non-zero average, that's when we end up using the RMS values. All right, so let's get back. Let's get back to the lecture review. All right, so spinning the wire in a constant magnetic field. Okay, how does it generate electromotive force? Change of magnetic flux generates electromotive force. That's the Faraday's law. All right, and what you do is you change the area exposed to a constant magnetic field. In essence, you're changing the area. So the relationship between the maximum electromotive force, which is this is known as the amplitude, and the frequency is a direct one. There's the frequency. There's the maximum electromotive force. So the faster you spin this thing is, the larger the electromotive force is going to be. Higher the frequency, higher the angular speed, higher the electromotive force is. All right, RMS value represents what? It represents non-zero averages.
I have a question.
Go ahead.
Where does the 1/√2 come from? Is that because it's like the sine of 45 degrees or what? Where does that number come from?
Okay, let's get back to. Okay, Nathan, are you asking? Okay, there's two ways I can answer it, and there's if I understood your question correctly, or I can, if I understood it correctly, there's one way I can answer it. If I have to interpret your question, there are two answers I can come up with. Okay. Okay, do you see how we made a transition from that formula to that expression? All right, so what this says is the power is going up and down. Okay, so this is your power, and the power is changing within this time period. Okay, so this is your time axis, and notice that the power goes up and down. All right, so the average power is going to be right in the middle. So whatever your power is, average is going to be that you're looking at. Does that make sense?
Yeah.
Okay, so which means that this equation that you're looking at, all right, so becomes, if you're looking at the average power, the sign of this expression is going to become 1/2. Okay, so this 1/2 that you're looking at can be expressed in terms of this 1/2. I can express it in terms of 1 divided by the square root of 2 times 1 divided by square root of 2. This is going to be the same as 1/2.
Okay, so it's basically because the power doesn't drop below zero the same way the voltage in.
That's exactly right.
Yeah. Okay, yeah. That's where I got confused. Thanks.
Okay, yeah, because I didn't think you were asking me this.
Yeah.
Okay,
no,
but yeah.
Thanks for explaining.
Okay, cool. Okay, so there's a mathematical way of going from here to there. All right, I'm more interested in, do you understand that the average of this is going to be right in the middle? If you understand that, then it's straightforward to do the transition without doing a lot of math. All right, so, I mean, average power is going to be 1/2 of P, and you know the P is like located here, right? That's it. It's going to be 1/2. Okay, the average power is going to be 1/2 of the maximum power that you can have. All right, so this would be the maximum power that you can have. Does that make sense?
Yeah, good.
Okay, cool. All right, so the lenses law is the only thing left over, I think. Okay, so we discussed everything else here. All right, before we go back to the lenses law, I want to finish up the discussion about the transformers. All right, so speaking of transformers, what purpose do they serve? The purpose of a transformer is obviously you increase the voltage, and when you increase the voltage, the current goes down. There are two ways you can transfer power: in the form of current, and then if you're transferring it in the form of current, now resistance becomes a problem, because the resistance is much of that power is going to be lost in the form of heating, which means that by the time the power gets to the consumer, not much of it is going to be available in the form of current. So that's a problem. The reason why that becomes a problem is because resistance is sensitive to the length, the distance. All right, so that's the distance between the power plant and the consumer, obviously. All right, the way to overcome that is obviously to transfer power in the form of voltage. The bigger the voltage is, less of it is going to be lost in the form of heating, because they try to make the voltage as big as possible, the current as small as possible. Smaller the current is, the less of that power is going to be lost in the form of heating, obviously. But for this to work, you have to use alternating current generators. Direct current is not going to work. So let's discuss the physics behind it. All right, so you up the voltage, you get a step-up transformer. Voltage is going to go up, the current is going to go down. In fact, these are like 500,000 volts by the time you get up there, so not much current is going to be available. And then as you start to get near the consumers, you step down the voltage, so the current is going to go up. So stepping down the voltage involves a step down transformer. Step down means the voltage is being stepped up. 8,000 volts is still too high. They reduce it to 240, and then by the time it gets to your socket, it's going to be 120 RMS, basically. That's what it is. All right, so when you have
It started with the best
utility
of
poles,
intention.
all right, so notice that you got a utility pole here. So usually you may have transformers.
It started with the best of intentions, and then everything went wrong. A cat had gotten caught on a utility pole, and after neighbors failed to talk it down, the fire department was called. But as one of the firefighters reached out to grab the recalcitrant feline, 15 minutes passed, and a man's life hung in the balance. And then he regained consciousness, suffering from severe burns to the hand. Amazingly, the cat survived without injury, and was last seen running from the scene 8 of his 9 lives shorter.
I'm actually really surprised that the fire department responds to this.
It started with the best.
If a cat goes up, the cat should be able to come back down. I've never seen a cat skeleton in a tree or on a utility pole
of
before.
intentions, and then everything
And the problem is obviously the voltage or voltage difference.
went wrong. A cat had got 15 minutes passed, and a man's life hung in the balance. And then he regained consciousness, suffering from severe burns to the hand.
I noticed that his ass lit up. All right, that's where the fan is. Highly resistive. And none of his friends came to his rescue for a long time. He must have volunteered for this one.
Amazingly, the cat survived without injury.
Cat will survive something.
And was left.
It's physics 1, guys. All right, so how does that transformer work? All right, study this, take out the time you need. Time's up. Okay, guys, you need to have a primary coil, which is connected to an AC generator. And then you have a secondary coil, which is not, it could be connected to whatever the electronics that you're using, but that's besides the point. All right, so by using a transformer, you got the primary coil, you got the secondary coil. I want you to notice that they're connected to each other using an iron core. I wonder why they use an iron core. How does that work? All right, here's where we are. Okay, so you got your AC generator. And so the AC generator is going to make the current go this way, and then this way, and then this way. It's going to go this way, and then it's going to go that way. All right, so the current, notice that there's a coil here. All right, so the current is going to go one way, and then it's going to change direction. It's going to go the other way. All right, so ignore the direction of the current just briefly. I don't care which direction the current is going. Let's pretend that the current is moving in a single direction. All right, so the current is moving in a single direction. So what will the current do? So you got this loop, and there's a current in this loop moving in this direction. So that current causes a magnetic field around it. So there's going to be a loop, and this current is going to create a magnetic field going into the loop in that direction. So in essence, every time there's current, it's going to create a magnetic field just doing this. You reverse the direction of the current, the magnetic field is going to reverse direction. And you change the direction of the current, once again, the magnetic field is going to change direction. They use an iron core because the iron is going to become magnetized. Every time there's current here, there's going to be a magnetic field going this way first, and then magnetic field is going to change direction again, and then it's going to change direction again, and then it's going to change direction again. So what happens to the iron core is going to become magnetized this way, and then that way, and this way again, and then that way again. The entire magnet, the entire iron is going to become magnetized. So what's happening is, because you keep changing the direction of the current, as a result, you create the iron to become magnetized this way, and then become magnetized this way, and then magnetized this way again. Notice that the induced magnetic field is being intercepted by the secondary coil. So what's happening inside the secondary coil? The flux keeps changing inside the secondary coil, right? So the magnetic field goes this way, and then changes direction, goes that way, changes direction, goes this way again. And every time there's the change in the strength of the magnetic field, there's going to be a current moving this way, and then moving this way, and moving this way. So the current is going to keep changing direction. So alternating current is going to change the strength of the magnetic field inside the coil, inside the iron core. And the change in the strength of the magnetic field within the secondary coil is going to induce current in the secondary coil. That's it. All right, so let's go to the animation and then watch that up to that point. So the animation